how do we predict the amount of intermolecular forces, or sometimes I refer to these as stickiness on the outside of the molecule? So how do we estimate this on a large molecule? So first of all, this boiling point, if you can do this accurately, you can correctly predict melting points. Like if you had like three molecules to compare, you can correctly predict melting points and boiling points relative to, the other molecules you'd be comparing them to. If you had like a list of three molecules, which we're going to get to by the end of this tutorial. Okay, so the two things to consider are the polar nature of the molecule. So can it do dipole-dipole, the molecule? So all you really have to do is scan the molecule and look for an oxygen, look for a nitrogen, or look for a halogen. It's most likely going to be polar. It's pretty simple. All you do is scan the molecule and look for these three types of atoms. Next, if you do see one of these, look and see if it has an H directly attached to the oxygen or an H directly attached to the nitrogen. If it has this feature, this by the way is called an alcohol functional group, or if it has this feature, an NH bond, which is called an amine functional group. If it has one of those features, it's going to do hydrogen bonding. Okay, so for either, the next thing to consider, and this is a little bit different than general chemistry, but if than what we learned last year, this is like one added thing. So for either dipole-dipole or hydrogen bonding, if it has a lot of oxygens, it's even more polar than if it had one oxygen. For instance, if you have CH3, CH2, CH2OH. Okay, you have one H, one OH on this carbon, so this molecule can do one hydrogen bond. What if you had a CH2 and this? What if this had an OH, this had an OH, and this had an OH? Okay, this has an OH, and on the last CH, this one has an OH. Okay, for every one molecule, this can do three hydrogen bonds. So that's what this asterisk is saying. So if it has more O's and N's or more H's and NH's, it's even more uh it's even more good at doing intermolecular forces, or does it more well or better. Okay. So and then also another feature is if they're more spread out and towards the end, it also increases its IMS or molecule stickiness, how well it sticks to itself. Okay, if you had a whole sample of it. Okay, so that's one thing to consider, polar nature. Um, can it do dipole-dipole? Oops. So can it do so can it do dipole-dipole or hydrogen bonding? Okay, all this stuff here is just a little bit more details. Okay, like, how good is the hydrogen bonding? How good is the dipole-dipole in it? The next thing to consider, so first is polar nature, dipole-dipole hydrogen bonding. The next thing to consider is IMFs. I'm sorry, it's LDFs is the other thing to consider. Okay, so LDF strictly depends on electrons. Okay, if you think back to that picture, the helium atoms. So the more electrons you have, the better dispersion forces it can do. Okay, so for example, um, methane, if we counted the electrons here, carbon has, and this is not valence electrons, this is total electrons. Carbon has six, and each hydrogen has one. So this methane would have a total of 10 electrons. On this next molecule, we have C25 and H52. So this molecule would have 25 times 6 plus 52. So this molecule would have over 200 electrons. Okay, and this is a gas, methane. This is a solid. So you'll see that both of these are actually nonpolar because there are no oxygens or nitrogens. So this is also nonpolar. But this one is a solid at room temperature, and this one is a gas, and it's strictly because of it having more LDS, because it has 202 electrons. Okay, the other thing to consider with LDS is the overall shape of the molecule. So if you have a spherical shape, it's going to be worse at LDS versus linear. So for example, if you have this molecule, this is called uh, this is called isobutane. Its condensed molecular formula is this C5H12. If we compare that to, so there's 5 carbons here. If we compare that to straight chain um, pentane, that's 3 carbons, 4 and 5, and the condensed formula is exactly the same, C5H12, C5H12. Well, this one boils. This one has way worse LDS because it's spherical versus this one, which is linear. Okay, and then there's more surface area. If we draw another one, there's much more surface area for this one to do. Well, let's keep it green here. There's much more surface area for this to do those momentary dipole interactions. Okay, versus if you have a ball like this one. So if we have another isobutane, okay, I'll make a circle around it so we can focus on the outside of the molecule. So this one doesn't have that much surface area. So when it's spherical like that, it doesn't have that many points of contact it can make. Okay, whereas if it's linear, it does. So um, I'll try this in class. We'll look up the boiling point of isobutane, or perhaps you could do it on your own. All you really have to do is type in isobutane boiling point, and then type in pentane boiling point, and you'll see that this one has a much higher boiling point because it's going to take a lot more heat to separate all of these intermolecular forces here. Okay, versus this one takes very little heat to separate those. So this one's going to have a much lower boiling point than this one. They're both relatively low, but this one you'll see is much lower, the isobutane. Okay, so this quick explanation is for your flowchart, and I'll attach this to the school website. So the first thing to do is when you see a molecule and trying to tell if, its intermolecular forces, there's two things to check. Check its polarity, okay, and ask yourself, is it does it have an oxygen? So is there an O, N, or halogen? Okay, I got a little bit ahead. So that's the first thing to do when you see a molecule. Look for these three things. Okay, if it does, it's gonna be polar. Okay, there are some exceptions where the shape makes it cancel, but for the most part on large molecules, it's going to be polar. Okay, now if it does have an oxygen or nitrogen, look to see if it has OH connected or NH connected. If it does, then it can do hydrogen bonding. Okay, and if it doesn't have, if it's just an O or an N, then it will do dipole-dipole, the molecule. Okay, the next thing, separate thing to look at, this is almost like you do these kind of separately. So the next thing to look at is LDFs. And one important thing to note about London dispersion forces, all molecules can do it because all molecules have electrons that move around on it. So whether it's polar or nonpolar, it can do LDFs. Okay. And it depends on the number of electrons. And this is I modify this all the time, these ranges, but this hopefully gives you a rule of thumb. And you really have to see a lot of examples to get good at telling these ranges. So if the molecule has less than 30 total electrons, I've found that it would be considered weak LDFs. Okay, so if it's 30 or less. If you have between 30 and 70, the LDFs are getting pretty strong. So I would consider it medium. Okay, and if you're more than 70, they're getting to be pretty strong, your London dispersion forces. Okay, and then the other thing to remember to consider with LDFs is remember to check the overall shape. Okay, and check to see if it's linear or spherical. Okay, and then I'll let you guys look at your handout. This is exactly what's on the handout. So these are the main three that we'll be looking at are these three. Okay. I might have made a small mistake earlier where I called ionic bonding an intramolecular. Some textbooks actually classify it as an intermolecular because the attractive forces are happening outside the anion and cation. So some books actually refer to ionic bonding as intramolecular. Okay, and then we have ion to dipole. This is like when things form aqueous mixtures. So what we're really going to be looking at are these three. Okay, on the examples we do in class. So let's look at an example. This is kind of what this is leading to. So we're going to compare these three molecules, dimethyl ether, propanol, and propane, and we're going to try to predict the boiling point. So the order of in which they boil. Okay, so first of all, I'm going to write these in a condensed formula so it's easier to count electrons. Okay, and then this one is CH3, CH2, CH2OH. This one is C3H8. Okay. Um, so I'm going to number these so I don't have to rewrite their names. 1, 2, and 3. So molecule 1 has, so in this chart right here, we're going to actually count the electrons and list the electrons here for all these for these three molecules. So CH3O CH3. I went ahead and I did this already. I counted all the electrons. This molecule has 26 electrons. Okay, and for polarity, we look at this molecule and look and keep looking, scanning, and ask yourself, do you see an O or an N? And we do. We have an oxygen right here. Okay. Next, we ask, is there a hydrogen directly attached to this oxygen? And the answer is no, there's not. So this molecule will do dipole-dipole. Okay. Next, we look at propanol, molecule number 2. Okay, so this molecule, we count the electrons and we have 34 electrons. Okay, and if we look at our ranges here, I forgot to do this on the previous one. The previous one was 26 electrons, so that would be considered small. On propanol, we had 34, so that would be considered medium because it's in this range. So let's go back to that example. So this would be considered small. This would be considered medium. Okay, next we look at it has an oxygen, and next we ask, so it's polar. Next we ask, is there a hydrogen directly attached to this oxygen? And there is. It's right here. So this molecule can do hydrogen bonding. Okay, and so I'm having an issue here where it keeps skipping slides. Okay, so next we look at molecule 3, which is propane. This molecule has 26 electrons, which falls into the small range. And then keep looking at this molecule, and I don't see any O's or N's, so there's no oxygens or nitrogens. So there's no high En atoms that might cause it to be polar. So this molecule is non-polar, so we write NP. Okay, sorry about the slides here. Okay, so let's try to rank these. This molecule is medium, molecule 2, on LDS, and it can do hydrogen bonding. So this is decent compared to the other two. And this is the best out of the other two. So this molecule would have the strongest intermolecular forces and would therefore take the most heat to try to separate. So this would be number one. It should be the hardest one to boil or the highest boiling point. It should require the hottest temperature to get it to boil. Okay, next we compare molecule 1 and molecule 3. So this and this are actually a tie, but this is better than this. So molecule 2 would be the next highest boiling point, followed by molecule 3. Okay, and then next we would go on Google and look these up, and Google shows and Wikipedia, I know it's like user based, but it's actually pretty accurate as far as science things go. So I don't know why anyone would log on to Wikipedia and then lie about like propanol's boiling point. So I don't know why anyone would want to do that. So it seems to be pretty accurate actually, source. So molecule 2, if we looked at molecule 1 boils at 97 Celsius. Molecule 2 boils at 34.6 Celsius, and molecule 3 boils at negative 42 Celsius. So we were able to accurately predict these. Okay, next is the last example, and I would like you guys to try this example. I was going to write the condensed formulas here so it's a little bit easier for you to count electrons. If you use the condensed or the skeleton review, you'll see that these each have one H because each carbon's making three dashes. So benzene, you'll see is C6H6, and then ammonia is NH3. So these should help you count electrons a little easier. So when you fill out this table here, make sure you list the number of electrons. So count the number of electrons and actually write that number here, here, and here. Okay. Um, and also this molecule. Now we haven't played around with our molecule kits, but this molecule is actually flat and it's planar, which really improves the surface area. Okay, so I'm giving you a hint that this molecule has excellent LDS. benzene. Okay, sorry about the slides here. I'm having an issue. Okay, so let's see if you can complete this example. And I'll see you in class.